Good morning, everybody. My name is Francisco Melendez. I am the technical expert and evangelist responsible for the robotics roadmap in the FIWARE Foundation. And today I am presenting this webinar, which deals with the main aspects of implementing, monitoring, and supervision applications of robotic systems using FIWARE and ROS2. So our goals for today are, first of all, in an overview section, being able to gather the essential background on ROS2 for FIWARE users and developers, and on the other side, on FIWARE for those that are new to FIWARE but have their background on ROS2. And then I will describe a possible approach to develop reusable and easy to maintain FIWARE IoT agents for ROS2. Some specific ready-made components exist, and we will learn what is their role and how to use them. And then finally, I will talk about a demonstrator, and we will cover the main aspects of setting up a basic web application which monitors and supervises a ROS2 system. So let's go for it. First of all, what is ROS2? ROS stands for Robot Operating System, but in fact it is not exactly an operating system but an SDK. It is a collection of utilities and features and middleware libraries that allow you to easily build modular robot application. And well, the rationale behind this second version of ROS is that in the very beginning, the first version was using a very custom middleware at the bottom layer, and this limited the robot operating system to academia and research projects. And now with ROS2, the underlying middleware is professional, real-time enabled one, DDS. With this new version, even the industry or the most robotics ambitious projects can build on this ROS2. And the good point is that ROS is all open source. In their official ROS website, this is, let's say, the formula of the robot operating system. They offer you the means to plumb your different robotics modules. It offers tools, ready-made tools for you to develop and debug these robotics capabilities, and it also accounts for a really active community which continuously develops robotics components using ROS. It is important to understand ROS via its main elements. The concept of ROS graph aims to cover all those elements, executables, and connections that are relevant to understand what is happening in the robotics systems. And here in the left, you have the list of these main elements. In particular, nodes are equivalent to processes or submodules of the robotic system. An example of a responsibility for a node could be being the driver of the motors of a mobile robot. A different node can be responsible for the localization system of the robot, and another one can be responsible for the navigation, for instance. Then one of the interfaces is the ROS2 topics, and these topics allow to implement publish-subscribe patterns. Then we have services. Services allow ROS2 system to implement request-response interfaces, and actions are an evolution of this request-response service because they allow for you to implement long-term task executions. So you have one request and multiple responses while the task is being executed. Finally, parameters allow you to somehow configure dynamically the behavior of a node at runtime. Today, our focus will be on nodes and topics with these two sub-elements, publishers and subscribers. As you see on the right, every single node can implement their subscribers and publishers, and the means to exchange data samples is via topics. Let's have a look at the ROS2 architecture. As I was explaining in the opening, at the bottom we have the hardware and then the operating system of the robotics system of our robot. In particular, ROS2 requires a robot or a computing device which is running one of these three operating systems: Linux, Windows, and Mac. And on top of it, ROS considers a DDS implementation. The default one being used in ROS2 is FastDDS, which, by the way, is one of the FIWARE generic enablers, and other vendors are offering this DDS implementation and some guidance on how you can set up your ROS2 installation to operate with their DDS implementation. On top of this DDS implementation, what ROS is offering is an abstraction of the DDS features in a way that multiple languages can easily implement their client layer. The default client libraries for ROS2 are the CPP and Python 1, but other libraries exist, like the Java or the one for JavaScript and Node.js. And in particular, the JavaScript one is really useful for the purpose of this webinar. On top of this client layer, the custom code of every user to create their application is operating. So we have now an idea of the ROS2, but let's also cover some basic concepts of FIWARE for this webinar. In FIWARE, every device, every concept that needs to be represented in the digital world is an NGSI entity. And these entities have a simple but powerful model, which consists of a unique ID, a type, and a collection of attributes. These attributes can be properties, data holders which describe something relevant of the entity, and relationships, which are links to another entity which can be attached with a semantic value. Then FIWARE Context Broker are the components which are able to manage NGSI entities and offer the NGSI API as a standard interface which allows highly decentralized and large-scale applications to work. We are focusing today on the NGSI v2 API, and this is because in the FIWARE Foundation we are now running a number of experiments with factories and system integrators using NGSI v2. And you should also know, if you aren't aware, that NGSI LD is the new NGSI standard, and the next iteration of this webinar will cover the same concepts updated to this new version of the NGSI standard. What I want to highlight here is that NGSI offers to you some basic operations using create, read, update, delete, some advanced NGSI operations to implement subscription notifications, something similar like publish, subscribe, and registrations, in which the device tells the broker whatever happens with these attributes, I am responsible for them, and if you query them, I will serve the data. If you update them, I will process the update. And well, as I was saying, we will rely today on Orion, which is the FIWARE Context Broker that we will be using in the demonstrator to use the NGSI v2 API. Some more advanced concepts are linked to the concept of IoT Agent. Here I have a quote of the FIWARE official tutorials. An IoT agent is a component that lets a group of devices send their data to and being managed from a context broker using their own native protocols. This is the key part. But then we have some more details, saying that they should deal with security aspects. We are not covering this today, but also provide other common services to the device programmer. And this is what we are doing today with the IoT agent for ROS2. I will try to explain how preparing the generic IoT agent to be able to easily handle some specifics of the ROS2 middleware makes the life of the device programmer easier. Other useful concepts also linked to IoT agents are this IoT agent node leaf. What this IoT agent node leaf brings to the table is a relevant and powerful way to keep your IoT agent up to date, because the IoT agent node leaf is continuously maintained and it updates the library every single way that the NGSI API is evolving. So you just need to care about your custom code, and then the IoT agent node leaf does the rest for you. It offers multiple utilities, but in particular today we are going to cover the device provisioning stage and how to operate with active and lazy attributes. It is also quite relevant, this utility, the usage of commands, but this will not be covered today. This will be covered in the next tutorial of this series. Finally, we have the FIWARE IoT agent for JSON, which is a FIWARE IoT agent that builds on the IoT agent node leaf for devices which are using a JSON-based protocol. And this agent offers a very interesting feature, which are the transport bindings, and they allow you to make your bridge for a new protocol even easier than using the raw IoT agent node leaf. So we will see a bit about this. And now let's jump into the integration of these FIWARE IoT agents with ROS2. Today we will cover only the integration based on topics, and our proposed approach builds on the ready-made FIWARE IoT agent for JSON. It takes advantage of the IoT agent node leaf and also of the transport binding features offered. And what we propose is to develop a new transport binding, in this case for ROS2. How are we creating this binding? We are using the RCL Node.js library, which is the ROS2 client for JavaScript, and then we are adding some custom code which implements inside the agent a ROS2 node. If you see in the figure in the right, we have the context broker, then the FIWARE IoT agent for JSON, which relies on the IoT agent node leaf, and then the transport bindings. With the FIWARE IoT agent for JSON, you have some default bindings, the MQTT, HTTP, AMPQ one, and what we have done is to create a ROS2 binding. This binding creates a ROS2 node, and the node joins the rest of the nodes being run in the robotic system, and all of them can interact using topics. In this approach, the mapping we propose between ROS2 and FIWARE are a ROS2 system, robots, or robotic station is an NGSI entity, and topics as data holders matches with NGSI attributes. So having this picture in mind, let's move forward. The use case we are dealing with is the monitoring and supervision of ROS2 system. So first step is how we provision the ROS2 system. The second step is monitoring the system using the active attributes, that is, attributes that are continuously being updated every time the topic receives a new data sample. And then we will talk about supervising ROS2 systems using lazy attributes. Lazy attributes has the possibility to operate in both directions, from the broker to the device and from the device to the broker. But in this case, the data in queries is only served when a new query arrives. It is not continuously sending data as in the active attributes, and when the attribute gets an update, the IoT agent is notified and then has the opportunity to process that update before actuating the system. So these are our steps in the use case, and this is the architecture we have built in our demonstrator. If you see, we have created a Docker Compose environment, which consists of our ROS2 IoT Agent, a FIWARE context broker, and a web application, which is a graphical user interface that will allow us to monitor the ROS2 system. In the part of the ROS2 system is implemented as the TurtleSim simulator. This is the most relevant simulator of ROS2 because every single ROS2 beginner uses TurtleSim in order to get familiar with the basics of ROS. So our graphical user interface will be able to mimic the behavior of the TurtleSim simulator in a web-based application. Then we have the browser to receive the graphical user interface, and we are using the Postman in order to set up the agent, to provision the device, and to create the necessary subscriptions in Orion. That's all from the architecture point of view, and I have a small video in which I will showcase how the demonstrator works. Now the first thing is to run the Docker Compose environment. This will activate the Orion Context Broker, the Mongo database in the backend, the ROS2 IoT Agent, and the web application server. Then we run the TurtleSim simulator. It will appear in a few seconds. This is the simulator. As you see, it's a very, very simple map with a mobile robot inside of it. Then we create our service group and we provision our device. Here I can point one important thing. It is not required this step of creating the service group in every single application, but in the next slide we will see more details about this. Once we have our device provision, the next thing we do is to subscribe to the changes of our simulator, and then what we finally have is our environment running with our web-based interface. If you see, the turtles are in the same position both in the ROS2 side and in the web application. And now what we are going to do is to teleoperate the turtle and see how both canvas are mimicking the behavior of the turtle. Pay attention to the second canvas, the one in the middle. It is moving slower than the first one. This is because we are using a parameter of the subscription, which is the throttling mechanism. The left one is using polling behavior, is continuously asking the broker for the new value in the TurtleSim post, but the other one is using subscriptions, and the throttling has been set to 2 seconds. In the case of the polling, I set the polling rate to 200 milliseconds, and it is continuously asking for these values. So this is the behavior of the application. And then let's go into what is happening in the internals of this demonstrator. So the first step was creating a service group. I was saying that this is not mandatory because the aim of this step is just to provide the agent with the information that is common to multiple devices that are sharing the same type. This way, you don't need to put that information every single time you are provisioning a device. The relevant part is in the provisioning step. In particular, here we have a way to provision active attributes. This means that when we provision an active attribute, every single sample that is published to the ROS2 topic leads to an update in the context broker. How we are approaching this? Well, to me, the name of the attribute is described as turtle pose, active in this way, and then we are adding metadata with some information that is specific to the ROS2 middleware. In particular, we are telling that the ROS2 interface that we want to use is a subscriber, that the type of the topic in ROS2 is the TurtleSim pose, and the name of the topic is /turtle1 turtle pose. This is the last thing. It's a very custom feature of this approach I am presenting today, and it's the throttling for the updates we are receiving in the context broker. And what this means? The subscriber in ROS2 will execute its callback every single time that new sample arrives to the ROS2 topic. What I am doing here is to tell my ROS2 callback in the subscriber that to discard those samples that are coming faster than 200 milliseconds. We are using metadata here to use this to add this information in the agent, to share this information with the agent, and the boundaries between defining this as metadata or a different approach which is considering them as internal attributes are a bit blurred. It depends on the use case. I am open to discuss with you if you have a use case in which you see them more as metadata or as internal attributes, but to me it is not that clear. It depends on the purpose. Let's move to the provisioning of lazy attributes in the ROS2 system, and here I am using the other approach, internal attributes. If you see, I am describing my lazy attributes in the same way as the actives, but now in the internal attributes I am using two different interfaces. One of them is subscriber, the one that monitors the turtle pose using the lazy attribute, and the other one requires a ROS2 publisher, which is set velocity. This way, every time we update the set velocity attribute, the ROS2 agent will be able to create a publisher and send the value in a topic that has the type geometry message twist and the name turtle1 CMD bell. So how we implement the polling pattern, this is the most basic pattern to monitor a ROS2 system, and what our web application, our graphical user interface displaying the turtle does is to continuously send a GET request specifying the ID of our ROS system and the attribute it wants to read. So this is quite simple, but the subscription notification pattern is a bit more complex, but really useful. What we did in the subscription step that was displayed in the video is to send a subscription to the context broker in which we are saying, please notify my application when the turtle changes its pose. We are giving the ID of the entity we want to subscribe to. We are saying that please send me the notification when a change happens in the turtle pose active, and then please send me the turtle pose active attribute to this URL, which is the server of my web application. Then we have this throttling parameter, which was telling the second canvas in our application to operate every 2 seconds. Then we can jump to the final part, which are the lazy bidirectional attributes. And for this, we have 2 relevant things. The first one is when you want to query to monitor what is happening in the ROS2 system. And here in the left side, you can see how the query looked like. And the relevant thing I want to tell you is that a function of the IoT agent node lib is our shortcut to easily develop our ROS2 IoT agent. We are using set data query handler in order to process the queries and interact with the ROS2 system. And in particular, the behavior that we have created for our demonstrator is that when the device is provisioned, the ROS2 device is provisioned, the agent creates a subscriber for the lazy attributes. And then this subscriber is created along with a cache that is storing the last data sample received by the subscriber. When a new query arrives, the query handler is responsible for retrieving the data stored in the cache and then serves it back to the context broker. This is the behavior we have implemented as a proof of concept of our ROS2 IoT agent. Then the final one is the most basic actuation pattern, which would be updating an attribute in the context broker, which translates into a message being published in the ROS2 topic. Our approach in this demonstrator works this way. When the system is provisioned, it creates an object which stores the topic type and the topic name of the lazy attribute, which is defined as publisher. And then when a new update arrives, the update handler is able to create a ROS2 publisher according to the internal attribute description and sends the data sample to the topic. And the function in the IoT agent node lib to implement this feature is the set data update handler. And you have links to the documentation right here. So our roadmap to extend the contents we have presented today is to extend the demonstrator with a ROS2 agent that actuates ROS2 systems using service and action clients and using FIWARE commands, automating the installation of custom ROS messages. For instance, in the case of TurtleSim messages, what I did is in the Docker image, I installed the TurtleSim packages in order to make use of the messages, but a similar result would have been achieved using volumes and then creating a ROS2 workspace inside the Docker environment. So my idea is to automate how you can share your ROS2 workspace inside the Docker image and then compile your messages using volumes. And then once this release is ready, we will create a FIWARE step-by-step tutorial with the improved demonstration and a new webinar. Other topics that are in the roadmap but will be addressed in the next iteration, showcasing the same concepts for the NGS ILD. Implementing a demonstrator which consider FIWARE-based historical data management and complex event processing for ROS2, and extending the agent for ROS2 parameters, service server, and action server features. In the meantime, please do not hesitate to contact me via email if you are working or are planning to work on a project which is related to these contents, or if you need help with other topic that is linked to the use of FIWARE in robotics and automation scenarios. Here I am giving you some useful links for the contents we have presented today. The first part gives you some insights on the getting started with FIWARE. The second part points you to the ROS2 documentation, which has a clear learning path, and you can get familiar with all the ROS2 concepts in case you need it. And then for developers of FIWARE IoT Agents, I am giving you the links to the IoT Agent Node-Lib and to the IoT Agent for JSON, and also for the RCL Node.js. So that was all, and just a little summary. Some little background on both FIWARE and ROS technologies is needed to use and develop ROS2 IoT agents. Then IoT agents which rely on the FIWARE IoT Agent Node-Lib are faster to develop and easier to maintain. The same happens with RCL Node.js, since the RCL Node.js JavaScript library offers ROS2 interfaces, and it easily works with JSON messages. Using the FIWARE IoT Agent for JSON in combination with the RCL Node.js makes our life even easier. And the good point is that in the same way that the IoT Agent Node-Lib maintains itself up to date with respect to the NGSI standard, the RCL Node.js does the same for the different ROS2 versions. So you only need to care about your custom code, and RCL Node.js and IoT Agent Node-Lib are doing the rest. Then the best approach to adapt the FIWARE IoT Agent for JSON for using ROS2 is developing a new binding for it, and it is necessary to share with the agents some ROS2 specific information. We have presented two approaches in the provisioning state using metadata and internal attributes. Finally, we have created a demonstrator which showcases how to work with ROS2 topics, and the demonstrator will be extended to work with services and actions using FIWARE commands. A new webinar will be created afterwards. And well, that was all from my side. I want to thank you for listening.